Hi everyone. I want to try another reaction in Unit 10, the amines unit, and that reaction or sequence of reactions is commonly known as the Strecker synthesis to make alpha amino acids. You might know that alpha amino acids are the building blocks of proteins, and I debated whether to put this Strecker synthesis in Unit 10 amines or wait until Unit 11, which is peptides and proteins. But I decided here we're going to focus on the synthesis, the organic chemistry. Unit 11, proteins, will focus more on properties and structure of large proteins, primary, secondary, tertiary, and quaternary structures. The organic chemistry, most of the organic chemistry is, I'm going to reserve it for other units. So we're going to do Strecker synthesis, a very, very popular um, topic on the MCATs I've heard. Before we move on, that's my nephew, Rami. He lives in Brooklyn. And Strecker is named after Adolf Strecker, uh, another German, who did his work in the mid to late 1800s. So it seemed to be a very productive time in Germany in the 1800s. And the Strecker synthesis, again, makes alpha amino acids. But why don't we first figure out what an alpha amino acid is? Let me double check my work. Okay, so I'm going to draw the amino acid with the amine part on the left, the acid part on the right, and we're going to choose an amino acids. There are actually 20 natural amino acids. Let me see. I pulled up a chart. So there's 20 there, and why don't we pick something fairly simple? Let's pick alanine. Okay, so I'm missing the methyl group, and the stereochemistry actually is going to be wedge for this group here. I called this, or I looked it up. This is alanine. And I specifically made it wedge because the stereochemistry for this, for most amino acids, is going to be S stereoisomer. But biologists, medicinal chemists, they know this as an L amino acid. Levo for Latin for left, S, I think Latin also for sinister. So it's all telling you the same thing, that we have one stereoisomer here, and it is the S version. Okay. Why amino acid? Well, here's the amino group. So here's the amine, but the group itself is called amino, and here you have a carboxylic acid. There's interesting acid-base properties here, but again, I'm going to reserve that until Unit 11. Why alpha? Because you go from the carboxyl group, and the carbon next to it is alpha. If there was more carbons, it would be beta. Interestingly enough, there are also beta amino acids. So this one is definitely an alpha amino acid. Do you know what a beta amino acid would look like? A beta amino acid would look like this, where the amino group is 2 carbons away. So that alpha is telling you where the amine group is. It's on the alpha carbon. So here, let's see what this would give us. I actually don't know which carbon the R group would be for very simple. Did I do beta? Alpha, oops, gamma. That's a gamma amino acid. Gamma amino acid. This was a bit fortuitous. You know what this is called? This is GABA. Gamma amino butyric acid. 1, 2, 3, 4. GABA is a neurotransmitter, a very important one. That was just totally by accident, but as long as we're here, it's a neurotransmitter that helps with coordination, muscle control. And if you have difficulty producing GABA or the receptors aren't recognizing GABA, then you start to have uh, diseases like Parkinson's, something where you kind of have tremors, like loss of muscle control. All right, so that's a gamma amino acid. All right, why don't we get to the STRECKER synthesis? Again, most of the amino acid talk will be for Unit 11, but let me show you. This is in honor of my nephew. I don't know if you can see that. So he's going to learn. See this alanine. They also have code names, and let me show you that. Alanine is the letter A. Okay. So I'm trying to teach my nephew the alphabet, but the alphabet in terms of amino acids. And let me just a little shout out to him. I hope you could hear this. I made it bigger, and you have to read me this protein sequence for the top, this line here. So what's the first letter? R. And R. Wait. R is for what? Arginine. Arginine. Okay. What's the next one? I is isoleucine. Isoleucine. Okay. Next. D. What? D. D. Wait. There's a D. Oh shit. Okay. We'll stop there. 4 years old, guys. So he'll be hopefully. Well, I don't want him to be a chemist when he grows up. Anyway, STRECKER synthesis. This is reaction. I don't know what reaction this is. We had Gabriel synthesis before. Let me just double check my old notes. We ended off with reaction D. So this is reaction E, 10E, STRECKER synthesis. STRECKER synthesis starts with an aldehyde. Okay, and why don't we do the STRECKER synthesis to make alanine, the amino acid alanine, A. So start out with an aldehyde. Okay. The R group, it's called the R group, or the side group, is a methyl group for alanine. And this is real easy. You're going to match this part right here. Should match the R group of the amino acid. So we have a methyl group off of the aldehyde. That's what's going to show up in the final amino acid. So matches the R group. R standing for the side group or the rest of the molecule. Okay. The first set of reactions are going to be, most textbooks have NH3 with hydrogen cyanide or hydrocyanic acid. Let me double check that. And then 2, maybe some type of hydrolysis because we have H2O, H2SO4, and some heat. Interesting. Okay, here's your dot. Well, heck, if this is the R group, it's connected to the alpha carbon, as we saw here. Okay. Not only that, what else is connected to the alpha carbon? The amino group. So things are going to be happening at this dot. We got to put a carboxyl group. We do have to put a carboxyl group and an amino group. Let me draw you the product, and then we'll go through the sequence, the mechanism. Dot. Wow, I should have practiced. Here we have the carboxyl group. And here we have the amino group. Okay. So this is alanine. It is racemic. Do you remember what racemic means? A mixture of enantiomers, in this case R and S. That's because this carbonyl group is flat, and when we're adding groups to it, they could add on either side, front or back. So this is not a great way yet to make the stereo pure compound. What people typically do is they take the mixture and they're able to purify it. We're not going to go over that. It's a very interesting process, how to purify enantiomers. But what is happening here? Is there anything that looks familiar? You know, we did go through in a previous unit the carbonyl chemistry, aldehydes and ketones. In this unit, amine unit, we saw this. Remember, this is going to form an imine. Imine. We know that cyanide is a good nucleophile. Okay, and then we're assuming that we do some type of hydrolysis. So this is what's happening. We have the aldehyde. Okay, I'm not going to draw the mechanism just yet, but if we take just the ammonia part first, and maybe we're thinking about this will also provide a proton, so maybe the pH is acidic. Okay, this is just a general plan. All right, we'll go through the mechanism a bit later. We get this, right? Don't we get the imine? Now we do have an H. Okay, we do have the imine. Now, because of this hydrogen cyanide, we are going to protonate the imine. And we're going to have cyanide attack. So we get, at some point, this intermediate. You see where we're headed towards? And then we have hydrolysis. What are we hydrolyzing? We're hydrolyzing the nitrile group. Under acidic conditions, so maybe we would have an NH3 plus here, but maybe we just have enough acid to do the hydrolysis and not the protonation. I'll have to decide, or I'll decide soon what to do. Yeah, let's do that. Because you are under acidic conditions, let's adjust this and make this protonated. Amines are basic, so they're going to grab that proton. No big deal. And then we have the cyanide or the nitrile group turn into the carboxyl group. Okay. You know the mechanism for at least up to this step here. I don't typically teach the hydrolysis of a nitrile because there's a ton of proton transfers because you have a triple bond to make and you have to eventually change that triple bond into no bonds to nitrogen. But let me show you, let me do one more example. Okay, let's pick a different amino acid and I'll draw you the mechanism. Okay. What amino acid are we going to look at? Let's go back to our chart. Again, there are 20 amino acids. 6, 11, 12, 13, 14, 15, 16, 17, 18, 19. Ah, good, 20. Let's take, I think Rami mentioned isoleucine, right? Isoleucine is right here in the middle. Oof, it has 2 stereocenters. I might have just bit myself in the ass. Okay, so let's try this. So let's say we have to make isoleucine. It is still going to be racemic at the alpha carbon, NH2. Isoleucine, and the abbreviation is I. Oh, you don't see that. Okay. What was the trick? The trick is, let's identify the alpha carbon. The trick is the aldehyde will have this group right here, the R group. The alpha carbon started out as the carbonyl. So I'm going to draw this in the same orientation so I don't get mixed up with this stereochemistry here. So I'm keeping that stereochemistry, and all I'm doing is I'm adding the aldehyde part to the alpha carbon. I'm not going to mark this alpha, okay? Eventually it will turn into the alpha carbon, but right now you know that for carbonyl compounds, the alpha is the one next to it. So don't mark this alpha. You can mark it with a dot if you want. Now, I've mentioned that the reagents could be this, but also the reagents can be, in practice actually, people mix these two chemicals together. Yes, those two chemicals together. By mixing these two together, you will eventually get this ammonia and hydrogen cyanide. Again, in practice, though, we mix these two. I'm not sure why. I think it's because we typically don't have a canister of gas, hydrogen cyanide gas. We make it within the round bottom flask. Then you have, we'll just do H3O plus and heat to hydrolyze. Okay. Okay, so here's the key. The R group stays the same. At that dot, that's where you will put the amino group, and I am going to keep it as protonated, and the carboxyl group. And you see that we match the isoleucine sample perfectly, except for the stereocenter is scrambled. Okay, so again, this is for CMYC. Shall we go through the mechanism? Let's see how far we get with the mechanism. I'm still debating whether I'll draw the mechanism for the hydrolysis of the nitrile, but it'll be worth showing the mechanism up to the imine. Okay. The way that I taught imine formation is we do a protonation step at first. Some textbooks don't do a protonation, but we're going to do a protonation. And like I said, at some point we're going to have HCN for here. So we could skip to that step right away and do HCN like this. I'll draw out the triple bond to remind ourselves. What are we doing? I almost attacked here, but no, we're going to protonate first. Protonate first. Technically, these are all reversible steps, but I'm not going to worry about that. Very interesting. Because, you know, that O is not this O, right? This O came from the hydrolysis of the nitrile. But anyway, we get this. Okay, that's what was left over. But we're not going to attack with the cyanide. We're going to attack with the ammonia to make, hopefully, an imine eventually. This is standard imine formation that you learned in a previous video in this unit. OH. Getting a little bit worried. Is this going to work? Oh, you didn't see that. All right. I like to do my proton transfers separately because you want to protonate this, but also deprotonate that. But I do them separately. Most professors do. Okay. I'll draw the triple bond. All right. I'll use this anion to grab this hydrogen. You could use water. You could use another ammonia. It doesn't matter to me. Good. My amine is now neutral. And we're going to pronate the hydroxyl group to make it a good leaving group. We do have HCN again. Let me draw it this way now. Okay. You can know there's a triple bond between those two atoms, but you don't have to draw the bonds for a line structure. You have to draw this bond for sure because you explicitly have to show you're breaking it. And this was brought in. Are we almost done? Okay. Do you remember how to kick out water in these types of reactions? You're using an internal lone pair, and you're kicking that out. Oh, this is good. What you notice here is that your nitrogen is still going to be protonated, and it's going to be positive. Normally, and we kicked out water. Normally, you would neutralize this and have just a neutral amine. Neutral imine. Right. So right now we have the protonated amine. Okay. Next, we created a cyanide ion in this step up here. We're going to use that next. Okay. What are we going to attack? We're going to attack. Oh, need a lone pair. And we're going to attack this carbon right there. Beautiful. Because that has the amino group, NH2. It also has a potential for a carboxylic gas when we hydrolyze the cyanide. Hydrolysis of cyanide. Let me go through at least a couple steps. Okay. We're going to protonate because eventually we're going to have to kick off nitrogen. Okay, so let's protonate that. This is going to take a while, okay, because there's a lot of proton transfers, but it's a good exercise. We're going to go, we may not hydrolyze the whole thing, but we'll partially hydrolyze it. Okay, weird looking molecule, right? But do you see what we're setting up? We're setting up an attack with water. So this is H2O. We created water actually in the previous step. So we're going to use that H2O and we're going to attack. Do you see now? Maybe not. But let me draw this intermediate, and you're going to see that, oh my goodness, we have so many proton transfers to do. Okay, so we added water, and that water, or that oxygen is still protonated. But look what we accomplished. Yes, so the carbon-nitrogen bond, which is now right here, turned into a double bond. And now this nitrogen is neutral. So we went from a triple bond to a double bond. Okay. I'm going to break one of my rules, only out of clarity and expediency. I'm going to protonate and deprotonate at the same time. Okay. Because look what we have now. We have this OH, and now we have a protonated imine. But this is the nitrogen from the nitrile. I almost freaked myself out there. We still have this nitrogen here. Okay. Interesting. Look at this. What do I want to do? The purpose is to try to get this bond to go away. So I went from a triple to a double, and now I'm going to go down to a single bond to nitrogen. I'm running out of space. Am I getting anywhere close, though? Can you see if I'm getting close to what I need to happen? So the thing is, I still have to make this a good leaving group. Oh, that's what's happening. We need another oxygen. We need a carboxyl group here. So I'm going to have to continue on the next page. Yeah, I was trying to figure out how that NH2 is going to leave eventually. So on the previous page, we left off with this molecule here. Okay. We're not going to do a proton transfer just yet. What we are going to do is we're going to try to get that second oxygen in place, right? We're going to hydrolyze this. So this comes in and hits that carbon, and we make that. Almost done. OH. Good. OH. Oh, man. See, this other oxygen from water has two hydrogens. Plus NH2. What is our goal? Our goal is to get rid of the NH2, keep both oxygens, make sure at least one of them will have a double bond. Let's do that again, that sheet where we do an internal proton transfer. Almost there. How do you think we're going to kick out this nitrogen? Again, internal lone pair. Ammonia is basic. That's acidic. Or I said amines are basic. That's acidic. Again, one last time, another proton transfer. It's really a protonation deprotonation in the same step. Something that I don't want to do, but again, this is super long, so I'm going to combine those two steps together. And finally, we got the hydrolysis of the nitrile completed. That's isoleucine, racemic version, because your alpha carbon can be R and S, R or S. Ooh, Strecker synthesis. The main point for the Strecker synthesis is that you figure out what your R group is on the amino acid, and let's pick a different one. Let's pick, hey, didn't mean to yell. Look at tyrosine. So now, could you predict what the aldehyde looks like to make tyrosine? And I'll leave you with that. Let me draw out tyrosine for us. And here's your take-home problem is tyrosine. How do you make by Strecker synthesis? That problem will be on the sheet of problems for this video. Video 10D20. Okay. All right. Good luck studying, and if you have any questions, you could leave them in the comments, or you can email me if you're in the class.